By definition, a solution consists of two parts, solute and solvent. Solvent. In the exam, if you would jot that down real quick, because the reason I'm showing you this is because it requires you to kind of think backwards about what's going on here. The way the question's worded, it is deals with the solute, but it's not asking you for the solute, it's asking you for the solvent. So in the context of the problem, since they're asking you for the solvent but giving you the solute, how do you approach working this problem? Keep in mind that the 22% sodium chloride is 22% of dissolved, but the rest of it is solvent. So the solvent percent is 100 minus 22%. Okay, 78% solvent. In this case, water. So it's asking you what mass of the solution is 22 of an aqueous 22% sodium chloride contains 70.5 grams of water. Well, the 70.5 grams of water is the 78% of the mass of the solution. That is 78% of solution mass is equal to water mass. And so that's 78% of X is equal to 70.5 grams, solving for X, 70.5 over 0.78 grams. So just take a look at that so you won't get skewed off into left field with that kind of problem. Okay, it's very specialized type problem, but it's there. It's different solution, but you want to think in terms of, well, what's given is not what they're asking for. Okay. Are colligative properties of solutions. What this refers to are properties that change, of solutions that change due to the presence of the solute that you dissolve in that solution. And the things that it will affect are boiling point, freezing point, vapor pressures, osmotic pressure. Those are your primary things that are changed due to the colligative properties. And in the context of what we're talking about are topics known as boiling point elevation, freezing point depression, so I've got a problem on that on the exam. I've got changing vapor pressure. Now hear me, vapor pressure itself of the solution is not a colligative property. It's a natural property. But change vapor pressure is a colligative property, and to change it, that is dependent on how much solute you add to the system. Osmotic pressure is the dilution tendency of a salt solution. And what I'm primarily getting out of the osmotic pressure issue is determination of formula weight of low molecular weight biomolecules. I got a problem on that. Using vapor phase osmometry. Okay. Determination of molecular weight of biomolecules using vapor phase osmometry. It's a very specialized thing, but I do have a problem. Specifically is the vapor pressure of solutions. If a solute is added into a solution such that the solute is compatible and does dissolve, okay? The solute interacts with the solvent to lower the vapor pressure of the solvent. That is solvent plus solute, lower vapor pressure. So if we take a container of solvent, now put some spaces in between your solvent molecules. Then we drop in a soluble solute. Then that soluble solute will interact with the particles and act to inhibit their evaporation. Okay, so that's the physics of what's going on. Vapor pressure above the liquid solution here is still due to evaporation of the solvent. Many of you have probably heard that, if you have a salt solution, you boil off the water, you got the salt still there. Well, the salt doesn't come out, or the solute doesn't come out as a vapor or something. This is the ability, the vapor pressure is the ability of that solvent to evaporate once the solute is in that system. Well, from a mathematical standpoint, the vapor pressure of a solution is given by what we call Raoult's law. Raoult's law. And the vapor pressure of solution is equal to the mole fraction of the solvent, which is a percentage of solvent relative to the total solute and solvent. We'll get to it in a second. Times the vapor pressure of the solvent. Now, it is this equation that we want to work with and manipulate in problems to get a change in vapor pressure, mole fraction. Is given by this capital X of some component I. This is a fractional value, mole fraction. That's exactly what it says. Given solution of 0.75 mole ethanol, in 1.97 mole solvent water, calculate mole fraction for ethanol and water. Now this is a percentage. What percentage? Add them up, and part over total kind of thing. But it's not times 100. So mole fraction, in essence, of the component is that moles of that component over the sum of all the individual components, from I equals 1 to n, however many you have in there, to however many components you have. So in this case, you have moles of ethanol, or let's do it this way. Let's just work it out. Moles of ethanol, keep wanting to go write it out. So we have 0.75 mole divided by the sum of those two, 0.75 plus 1.97 mole. See what I did? Part over total, and then we get a number. Well, you can do the water mole fraction two ways, 100 minus whatever you get here, or repeat this procedure but use the moles of water. Okay. That's 0.75. .72, take the reciprocal times 0.75, 0.276, 0.276 minus plus 1 equals that's 100. 1 minus that minus 0.276, 0.724. See, those are just really percentage numbers that you didn't multiply by 100. Everybody okay on that? Okay, so it's simply convert to moles, add the moles up, and take the individual components, right? And just one at a time. It's like a percentage, part over total. Everybody good? Okay, we're going to have to add to this. Was just given by Rayleigh law to be the solvent component, if it's given, usually it's not given, times the vapor pressure of the solvent. See that? So you've got, now, second thing is the mole fraction of the solvent. I just showed you that, plus the mole fraction of the solute, always equals 1. That's what I showed you, and that's why we were able to do this down here. Okay? So those two are combined simultaneously in this through the solvent. So X of the solute, X of the solvent is equal to 1 minus X mole fraction of solute. That is substituted in here, and you get the next equation. Vapor pressure of the solution is equal to 1 minus X solute. Clean that up. Times the vapor pressure of the solvent, which you distribute the vapor pressure of the solvent through this parenthesis, and you get vapor pressure of the solvent, which is mole fraction of the solute, times the vapor pressure of the solvent. This portion that I just bracketed is your vapor pressure lowering factor. That is the colligative property. Okay, calculate the vapor pressure of a solution that consists of 20.2 grams of sucrose and 70.1 grams of water. And this is your normal vapor pressure of water without the sucrose in it, or sugar. Formula weight of sucrose C12H22O11 equals 12 times 12 plus 22 times 1 plus 11 times 16, that's 144, plus 22 plus, I don't know what 11 times 16 is. 176 plus 22 plus 144, that's 342. So moles of sucrose is 20.2 over 342 mole. And that's 0.059 mole. Water is 70.1 over 18 mole. That's 3.89 4 mole. Sum of moles is 9, 10, 11, 12, 13, 10, 15, 8, 9, 3.953. So the mole fraction of sucrose is 0.059 mole out of 3.953 mole. And that's 0.015, and you don't have units on mole fractions. So the change in vapor pressure is the mole fraction of the sucrose or solute times the vapor pressure of the solvent. Well, we got the vapor pressure of the solvent's 42.2 from the problem back up here. So that is 0.015 times 42.2 millimeters. And so that's a 0.630 millimeter change in vapor pressure. Okay? So the vapor pressure of the solution now is the vapor pressure of the solvent minus the change in vapor pressure, which is 42.2 minus 0.63 millimeters of mercury. So that's one type of problem you need to deal with. And that is a 41.6 millimeters mercury, which is the solution vapor pressure in that. So you're going to have a problem like that you'll have to deal with. But that is the colligative property, not just the vapor pressure. So please go back and look at that and look through the problems I sent you, see if you can find some. Boiling point, elevation, freezing point, depression comes from your phase diagram shift when a solution is made. Phase diagram of water, as I've shown you in the last chapter, looks like this right here. However, when a solution is made, the phase diagram shifts down the sublimation line, and you wind up with a trend like this. And so the blue line is a result of the shift in the phases due to the presence of the solvent. Then you recall we drew a line at the atmospheric pressure. I'll throw this one in there. Well, like this. This is 1 atmosphere right there. Now, what I want to show you is that if you drop a straight line down from the normal curve to here, that's your normal boiling point. No, normal freezing point. However, if you drop that line from the blue line down, this is your solution boiling point. I mean, freezing point. Duh. Notice that he shifts to the left from red to the blue. That is called a freezing point depression. That's a colligative property. This is a change in TF. Delta TF is freezing point depression. And that is a colligative property. On the other side of this, if I did the same thing and came down from the 2 lines, I'd have the normal boiling point and the solution boiling point. Notice that it increases from left to right. That is a delta TB, boiling point elevation. Delta TB is boiling point elevation. The boiling point elevation and the freezing point depression are found in a little simple formula. Delta TF is lowercase m dot, m dot KF, which is a constant called the freezing point depression constant, is given in the problems, or delta TB, which is m, lowercase m, KB. KF, freezing point depression constant. KB is boiling point elevation constant. For water, well, their different substances have different K values. I think the KF is a minus 1.86 degrees C per mole. I'll have to show you what that is. Molar solution. And the KB is a plus 0.8 something. I'm pretty sure. Never enough time in the world. .86, yeah, I got that one. 0.512. A molar solution, different from molarity, is moles solute. You know how to calculate that, divided by kilograms of solvent. It's not kilograms of solution or grams of solution or liters of solution this time. It's moles per kilogram. Why? Because the system is going through a thermal history. this is constant in the process. 2.38 grams NaCl in 0.123 kilogram of H2O gives, that's 58 grams per mole, gives 2.38 over 58 mole over 0.123 kilograms. And that's a molar solution. That's a 0.334 molar, 0.334 m molar solution. Well, what's important is that this number times whatever you're given here tells you what that drop in freezing point is. So if you have a 0.334 molar solution, the change in freezing point is molality times Kf, which is 0.334 mole, times the minus 1.86 degrees C per mole. That drops, and so the product of those two tells you how much the normal freezing point drops. Same way on the boiling point end. So this will drop by 62 degrees C. So a 0.334 mole sodium chloride solution that we just made up here has a freezing point of a minus 0.62 degrees C, because we were able to calculate using the freezing point depression expression up here. Boiling point does the same thing. You just multiply your molality times that constant and tells you how much to add to the normal boiling point. The last topic, give me 5. Oh, we're not through till 10:15 anyway. Good, I'll go through real slow. Never mind. Osmotic pressure. I keep wanting to quit 10 minutes till. The symbol for osmotic pressure is a capital pi symbol. And what it gives you is the osmotic pressure equation. Solutions, when they contain a solute, have a variation in osmotic pressure. That is the ability to dilute. And I'll show you. Pi equals molarity times R value, that's your gas constant, 0.08206, times the temperature in Kelvin. Well, the problems that you have here is what we call osmotic vapor pressure osmometry. It's an instrument in which you make a solution, put it into this instrument, and it measures the change in vapor pressure caused by the molecule that you put in solution. Osmotic pressure, I'm sorry. And allows you to make calculations of mole rate of that molecule. So there's a problem. Now, if the osmotic pressure is molarity times the gas constant times the temperature in Kelvin, what is molarity? Moles over volume in liters. Moles per liter. times R times T in Kelvin. Now we'll find formula weight in the definition of moles, which is gram mass you're dissolving divided by that formula weight. So I'm going to solve this for the moles is equal to osmotic pressure times volume in liters, and multiply both sides, transpose, divided by R, and also divided by Kelvin temperature. Now moles is a mass in grams divided by the formula weight. So now this is then solved for formula weight, which is mass in grams times the gas constant times temperature in Kelvin, and that's divided by osmotic pressure that they give you in the problem, divided by the volume in liters. Okay, so it's another plug and chug type problem. Let me see if I can find it. Saffron is contained in oil of sassafras and was once used as a flavor of root beer. Given at 2.39 milligram sample, I've been 1,000, which is equal to 2.39 times 10 to the minus 3 gram, was dissolved in 103 milligrams of diphenyl ether, oh, this is from freezing point, boiling point depression. Wait a minute, that's the wrong kind. Dextrin. Let me do this one. Sorry, take that out. You can also get formula weight from freezing point depression, boiling point elevation problems. Solve molality for moles over kilograms. And then moles again give you formula weight. Here it is, dextran. Is a polymeric carbohydrate produced by certain bacteria to use a blood plasma substitute. An aqueous solution contains 0.582 grams of dextran, 0.582 grams in 106 milliliters of water. No, it says solution, sorry, not solvent, which is 0.106 liter at 29 degrees C, 294 Kelvin, and has an osmotic pressure 1.47 millimeters. And that is equal to 1.47 over 760 atmospheres, because you have to have it in the same units as R value. Double 019. So we'll use this formula weight expression derived up here. Keep it on the board right there. Plug and chug. And we've got, of course, our value is 0.08206. So our formula weight of our dextran molecule starts out with, where'd our mass go? 0.582 grams. R is 0.08206 liter atmospheres over mole Kelvin. Temperature is 294 Kelvin. I'm going to divide that by osmotic pressure in atmospheres. And the volume is 0.106 liters, and all that's given. So Kelvin drops out, atmospheres drop out, liters drop out, we're left in grams per mole, which is what we should be getting. And so I get absolute calculator answer 69,718 grams per mole. That's a polymer. And so this is a 3 sig fig problem because of the mass number here. So we would want to use 3 sig figs, 69,700 grams per mole. Gotta love y'all, guys. Thank you so much for taking my course.